Hi everybody, Captain Al speaking with your bonus video for January for the full captains. It is on the electrical system. There's actually two videos. The first video is from a couple of years ago. You should watch that first. That'll act as a good primer for the electrical system. And then watch the bonus video second. The bonus video is going to cover the electrical system from a schematic standpoint. Then we'll look at the panel operation. And then after we complete that, we'll look at the synoptic display. And we'll finish up with a system Q&A. You have the electrical handouts, 4 of them, that are in your captain section that have been put in there. And you should follow along. The electrical schematic is not bad, but it's got some problems in it. So you're going to see here that I've corrected some things when we go through. We'll start with the DC system, and then we'll go to the AC system after that. We're going to assume that the airplane is unpowered, no power at all on the airplane, and then we'll take it from there. So let's take a look at the DC power system of the 747-400. On the 747-400, you have 2 batteries. You have an APU battery and a main battery. And those batteries are hardwired directly to a APU hot battery bus and a main hot battery bus. There is no switch for that. As long as you have battery power, the hot battery buses are powered. So before you have any power on the airplane, the hot battery buses would be powered. When you go ahead and turn the battery switch on, you'll be closing the battery contactors, and then power would be allowed to flow from the main battery through the main hot battery bus through the battery contactors to power the main battery bus. There's 4 battery buses. There's the APU hot battery bus, the main hot battery bus, the main battery bus, and the APU battery bus. So 2 are hot and 2 are strictly battery buses. But when you turn the battery switch on, you're closing the contactors, and so power will flow from the main battery or the APU battery through the respective hot battery buses, through the battery contactors to power the main battery bus and the APU battery bus. So those 4 buses are powered when you turn the battery switch on. You'll notice I took the number out of here because there's that number that was in there, whatever it was, is not correct. So just note that or scratch it out. Also, number 2 here would be the battery contactors, and the battery contactors would both be closed when you turn the battery switch on. And that would allow power to flow through the contactors to power the main battery bus, through the contactors to power the APU battery bus. Now, the next thing you usually do on the electrical power-up procedure is you usually turn the standby power selector to auto. And when you do that, that will then allow the main battery and the APU battery to power the APU standby bus and the main standby bus. In order to do that, they have to go through a inverter. The inverter will change DC power into AC power. And then that AC power can be used for the standby buses for the main and the APU standby bus, which require AC power. So when you take the standby power selector and you turn it to auto, the power will then flow from the main battery through the main hot battery bus, through the battery contactors to power the main battery bus, but that will also power the main standby inverter, which will convert DC into AC. And then this contactor, which is will be AC power, so I'll color it red here. This contactor would close when you bring that standby power switch to auto. Because there's no other power source for the standby buses right now other than the battery. The normal power source is AC3, AC1, and then the battery is the backup for the standby AC buses, both the main and the APU. So when you bring the switch to auto, this contactor would close, and then that would allow power to flow from the inverter and then go ahead and go up to the standby buses. And you can't quite see it here, but you can see right here is where we go to the standby buses. The APU battery would power the main hot battery bus, would go through the contactors, power the APU battery bus, but it would also power the APU standby inverter, which is going to convert DC to AC through the contactor for the standby power selector, which is number 1 here. And note that I did change that. They had number 1, I think, here somewhere, but they actually had the numbering wrong here for what's what. Number 1 here would be the standby power selector, and that power would then flow to the APU standby bus. So in this case, now you'd have not only the 4 battery buses powered, 2 hot and 2 main, or the APU, but you'd also have the 2 standby buses power the APU and the main standby bus as well. Now notice here, you might take note of this, that I highlighted this blue because actually this should be blue, not red, because blue is DC power. And then it's converted to, this should be red. It's converted to AC, so this part of it should be red, not blue. So whoever did this diagram really didn't think it through very well, because you should reverse these 2 colors actually. And then you have the red AC power going to the standby bus. The same thing here. The APU, this part of it should be blue, and this part of it should be red because you're converting DC into AC. So an inverter will convert DC into AC, and a transformer rectifier will convert AC into DC. So as you can see with the transformer rectifiers up here, the AC buses will be converted to DC power through the transformer rectifier. So DC bus 1, 2, 3, and 4 get their power from AC bus 1, 2, 3, and 4 through 4 transformer rectifiers, which will again change AC, which is red, into DC, which is blue. So these are correct. Up here, the TR colors are correct. What's not correct is down here, the main and APU standby inverter. The DC buses also, their power then will flow through what's called a DCIR, a DC isolation relay, and that power would then be put on the DC tie bus. So you have actually two buses, tie buses, if you will. One's a DC tie bus, and the other one is the AC bus tie breaker. As long as the bus tie switch is in auto, then the DCIRs are closed, like you see here. Yeah, they're showing closed as they are right here, and that would allow power to flow through the DC buses, through the DCIR, to power the DC tie bus. Now normally, before we leave DC power, you can see here that normally the power source for the main battery bus and for the APU battery bus is normally DC3. So when you're flying and DC3 is powered, let me get this out of here. Let's get that out of there. So when DC3 is powered, you'll notice that the power will come like this, and like this, and that contactor would be closed, and like this, to power the main battery bus. And then DC3 power would go like this, and over this way, and down this way, and over that way, and then come down here to power the APU battery bus. So the battery buses are normally powered, go back to that triangle. The main battery bus and the APU battery bus are normally powered in flight when all the engines are running and everything by AC bus 3 through the transformer rectifier to power DC bus 3. And then DC bus 3, as long as it's powered, will go ahead and power the main battery bus and the APU battery bus. The hot battery buses, their normal power source when everything is running would be the battery chargers. The battery charger, in essence, is like a transformer rectifier. It takes AC power, changes it into DC power, and then that's also going to keep the battery charged. So this is coming from, can't see it right now, but this power right here is coming from AC bus 1, and the power right here is coming from AC bus 1, and that allows the battery chargers to be powered. And then the battery charger, AC is converted into DC through the main hot battery bus and then into the battery to keep the battery charged. So the normal power sources when you're in flight for the main and the APU hot battery buses are AC1 through the ground service bus, through the battery chargers, through the hot battery buses to power to charge the battery. The main battery bus and the APU battery bus are normally powered by DC3. And that's how those buses are kept, that's how the batteries kept charged, and those battery buses are kept powered in normal flight. And let's see, I think that's it for the DC power system. So let's move to AC. And now let's take a look at the AC power system. The AC power system consists of 4 IDGs, that stands for integrated drive generators, 4 AC buses, 1 ground handling bus, 1 ground service bus, 1 main deck handling bus if it's a freighter, 2 instrument transfer buses, a captain instrument transfer bus and a first officer instrument transfer bus, 4 transformer rectifiers, 1 main standby AC bus, and 1 APU standby bus. So again, let's assume that we've turned the battery switch on. We've turned the standby power to auto. And we are going to establish AC power. We've gone through the electrical power-up procedure, but now we're going to go ahead and establish AC power using external 1, since external 1 is plugged into the airplane. If external 1 is plugged into the airplane, this contactor would close, and that would allow external 1 to power the ground handling bus. So it would kind of go like this, to this, to this. And all that has to be is available in order for it to power the ground handling bus. It doesn't have to be selected on. If we want to select external power 1 on, then we can take the switch and we can push it. And the available light, of course, indicates that the frequency and voltage are acceptable for use. And when you push external power, then we'll have external power 1 flow from here. Onto the AC bus tie. The split system breaker, since there's nothing else on the airplane, the SSB would be closed, and that would allow external 1 to power the whole AC bus tie. In addition, the power would be allowed to come through the contactor and power AC bus 1. The contactor here, number 6, would be the AC bus tie breaker. So as long as the switch is in auto, this bus tie breaker would be closed, and that would allow power from external 1 to go through the bus tie breaker to power AC1. And external power would also flow through the bus tie breaker and allow AC bus 2 to be powered, and external 1 through the split system breaker would flow through the bus tie breaker to power AC3, and then external 1 would power through the bus tie breaker AC bus 4. So all four AC buses now would be powered. AC1 in turn then would power its respective TR and convert that AC into DC in order to power DC bus 1. And AC bus 2, of course, would be allowed to flow through its TR and then convert AC into DC to power DC bus 2. And likewise, AC3 would power its TR, and that would convert AC into DC for DC3. And then AC bus 4 would be allowed to power its transformer rectifier, converting AC to DC, and then power DC bus 4. And then, like we talked about, the DC buses would then go through the DC IRs to power the DC tie bus. So this is sometimes referred to as the synchronous bus right here, which is really the AC bus tie, if you want to think of it that way. Well, we call it the synchronous bus. And as long as you have one power source like external 1 on the synchronous bus, the SSB, the split system breaker, would close and allow external 1 to power all four AC buses, which would in turn power their TRs, which would in turn power the DC buses. Now, if you had external 2 available but not selected on, power would be allowed to flow through this contactor and power the main deck cargo handling bus. So if you had external 1 available, remember external 1 could power the ground handling bus. And things that are on the ground handling bus would be things like the fueling panel, aux pump 4, aux pump 1 of hydraulics, the lower lobe cargo handling equipment, and the lower lobe cargo lights and things like that. So the ground handling bus can only be powered on the ground, and all that needs to be powered is if external 1 is available. It doesn't have to be selected on. If we had selected external 1 on, like we did here, then you get the power that we just talked about. But if external 2 was also plugged in and it was available but not selected on, then that would automatically power the main deck cargo handling bus. And that cargo handling bus would handle the main deck cargo equipment and the lights and the rollers and the everything that's in the freighter on the main deck. And that way the loadmaster and loaders could load the airplane as long as external 2 is available but not selected on. If you were to select external 2 on now, then external 2 would come on the right side of the synchronous bus, and that would cause the SSB to open, and then external 1 would power the left side of the synchronous bus, and external 2 would power the right side of the synchronous bus. But what that would do is kick off the main deck cargo handling bus because you only have one power source. If we had the APU running, that'd be okay, because then the APU would be available, and that could also power the main deck cargo handling bus. So if you were to select external 2 now and kick off the main deck cargo handling bus, you're going to hear from the loadmaster. He's going to come up front and say, "We're trying to load, what's going on?" So in the case of just having external, you're going to have external power 1 selected on, and external 2 will be available, allowing the main deck cargo handling bus to be powered so they can load the airplane. Now, as soon as you start the APU, then you could go ahead and switch to external 2 if you wanted to, or select APU 1 and APU 2 and have external 2 be available, and that would power the main deck cargo handling bus. If we did start the APU, once the APU is up to operating speed, then that would go ahead and provide power. But if you have APU 1 and external 1 both available, the priority is going to be external power 1. It likes that over APU 1. It's got priority. So external 1, even though the APU is running and the APU generator 1 is available, it's not going to power the ground handling bus. The external power 1 would. If you select APU 1 generator on, then APU would kick off external power, and then APU 1 would provide power for the left side of the synchronous bus, and external 2 would provide power for the right side of the synchronous bus. Or, again, if you didn't have external power 2 selected on, you had just had it available because you want it to power the main deck cargo handling bus, then APU would power the whole synchronous bus, and the split system breaker again would close, allowing APU 1 to power the whole synchronous bus. All it did was replace external 1 when you selected the APU on the overhead panel from the available light, indicating again frequency and voltage are good, and we've replaced external 1 with APU 1. And again, external 1 is still available, so it'll still power the ground handling bus. The ground service bus can be powered on the ground or in the air. And the ground service bus, things that are on that would be things like the battery chargers. That's the big thing, the 2 battery chargers. Miscellaneous service outlets would be on the ground service bus. I think there's some flight deck floodlights on the ground service bus. I think there might be some navigational lights on the ground service bus, and maybe a fuel pump or 2 that's on that ground service bus. The ground service bus again can be powered in the air or on the ground, but in order to power it, you do need either AC1 to be powered, and you can see here that if we do have AC1 powered, if we selected external 1 on, then AC bus 1 would power the ground service bus through that switch. And as long as AC1 is powered, this contactor would open, and then power would come from AC bus 1 to power the ground service bus to power the battery chargers. The ground service bus can also be powered from a switch that's on the flight attendant's panel at door 2 left, or in a freighter it's on the switch panel that's located on the aft of the flight deck. We'll also notice that you have 4 integrated drive generators, and the integrated drive generator is a generator and a constant speed drive all in one unit. It's self-housed, it has its own oil supply, it's very easy to change out for maintenance. So it used to be those were 2 separate things, a constant speed drive and a generator. on these airplanes, they combined it into one for not only more efficient use, but also the ease of maintenance if you have to replace one. And once the engine is turning, then the constant speed drive would operate. When it's up to enough speed, the generator would operate. And then the generator control breaker, when the IDG is up to speed, the generator control breaker would close, and then that would allow the IDG to power AC1, or IDG 2 to power AC2, or IDG 3 to power AC3, or IDG 4 to power AC4. So once the engines are up to operating speed, or once they start turning actually, then the generator would start to get excited. The field would be closed, and then the generator breaker would close when the IDG is up to speed, and that would allow AC bus 1, 2, 3, and 4 to be powered from the IDG. So let's take an example now that they are finished loading the airplane. So if we were now to select APU 1, which we already have on the left side of the synchronous bus, and let's say we select APU 2, and the APU would then power the APU 2 would power the right side of the synchronous bus. APU 1 would provide power for the left side of the synchronous bus, and the split system breaker would be open because they're two unlike power sources. They can't synchronize with each other. And now external 1 would be available and external 2 would be available. And as long as external 2 is available, it's powering the main deck handling bus. As long as external 1 is available, it would be powering the ground handling bus. Now, of course, at some point we're going to have them remove external power. So once we have them remove external power, then external power would be gone. The available lights would extinguish. And now we're running on the APU. Again, APU 1 powering the left side of the synchronous bus, APU 2 powering the right side of the synchronous bus. All 4 AC buses are powered. All 4 DC buses are powered. And as long as AC bus 1 is powered, then the ground service bus would be powered. The battery chargers would be powered, and then the battery chargers would be providing through the hot battery buses would be providing the battery with charging, so they're not discharging. Now, if we're ready to start engines, once we start engine number 4, and that's usually what we would do on a manual start, is start engine number 4. On an automatic start, auto start, we start engines 3 and 4. When the IDG is up to speed, the generator control breakers would close, and that would allow then the IDG to power AC bus 4, and this IDG for number 3 to power AC bus 3, and then that would go ahead and kick off external 2 automatically, and the split system breaker here would remain open, and engines 3 and 4 would be running, or just engine 4, depending on whether you're doing a manual start or an auto start. In this case, let's say we're doing an auto start. So now we have engines 3 and 4 powering the synchronous bus, and on the right side, on the left side, we have APU generator 1 powering the left side of the synchronous bus. But now we're going to go ahead and start engines 1 and 2. So once you start engines 1 and 2, again, when the IDG is up to speed, the GCB, the generator control breaker, will close. That will allow the generator control breaker to power AC1, and in turn, that would kick off APU 1 automatically, and now generator 1, or AC bus 1, would be powering the left side of the synchronous bus, and of course generator 2 through the IDG, the GCB is going to close, AC bus 2 is going to be powered, and that will automatically hook itself up through the bus tie breaker, would hook itself up to the sync bus. And then you'd have the AC bus 1 and 2 powering the left side of the synchronous bus, AC bus 3 and 4 powering the right side of the synchronous bus, and now they would synchronize all with each other because they all are like power sources and they can synchronize with each other, and the split system breaker would close automatically. You'll notice AC3 will normally be the power source for the captain's flight instrument transfer bus. And that's all basically the essential instruments for the captain. AC bus 2 would be the normal power source for the first officer's instrument transfer bus. But AC bus 1 is standing by with this contactor open. If AC3 were to fail, then the captain's flight instrument transfer bus would automatically switch to AC1. The contactor here would close. Or if AC2 were to fail, the first officer's instrument transfer bus would transfer to AC1 and that contactor would close. So the normal power source for the captain's flight instrument transfer bus is AC3, for the first officer's flight instrument bus is AC2, and the backup for both is through the these contactors. Which would normally be open, but would close automatically if these lose power, so they're protected in essence. Now also the AC3 will be the normal power source. You can follow it down here again. The engine IDG is powering AC3, and AC3 will be the normal power source for the main standby bus. And the APU standby bus, its normal power source would be through the captain's flight instrument transfer bus, which is being powered by AC3 as well. So really the power source for the APU standby bus would be AC3. So the main standby bus and the APU standby bus are normally protected by AC3. If AC3 fails with the standby power selector in auto, it automatically will switch to AC1, and then AC1 would power these standby buses through the ground service bus, and if you remember that diagram down below, it would go through the battery chargers, through the battery switch, through the hot battery buses, the battery switch, and then through the inverter to convert DC to AC, and then the power would come up this way to allow that AC1 to power the APU standby bus and the main standby bus. Now, if AC3 and AC1 fail, if that fails as well, with the standby power selector in auto, now basically the battery chargers, the ground service bus is out, the battery chargers are out, but the main battery would now take over through the hot battery bus, through the battery switch, through the inverter to power the APU standby bus and the main standby bus. So the standby bus is protected. It goes through 3 different channels. AC bus 3 is the normal power source. It fails, AC bus 1 takes over through the ground service bus and that whole route. And then if AC1 were also to fail, now the battery takes over. The main battery takes over through the hot battery bus, through the battery contactors, which is the battery switch, through the inverter, converting DC to AC, and then powering the APU standby bus and the main standby bus. And again, as we talked about, the transformer rectifiers would normally convert that AC to DC, to power the DC buses, and then as long as the bus tie switch is in auto, the AC bus tie switches would close, and also the DCIRs would be closed. So hopefully that it was not too confusing, and a little discussion through the schematic on the AC power system. Looking at the electrical system, you have on the right side of the screen here, you have the overhead panel, and this is the electrical portion of the overhead panel. On the left side, you have the system synoptic for electrical, and that is on the lower display unit or secondary ICAS. You'll notice they look very much the same, because the electrical system on the synoptic and on the overhead panel are pretty much a depiction of AC power and not DC power. You'll notice that in this case the engines are running. AC bus 1, 2, 3, and 4 are powered by their respective IDGs. The engines are turning, so the IDG is operating. The generator control breaker will close when the IDG is up to speed and then power the AC bus. The AC bus in turn will power its own utility bus through an ELCU or electrical load control unit. The ELCU's job is to measure demand, and if the demand becomes too great, then load shedding could take place. If load shedding did take place, you would see the utility and or the utility and galley buses turn amber and shed. In the freighter, there's only utility buses. The galley is hooked up to one of the utility buses. In a passenger airplane, you would have 4 utility buses and 4 galley buses. During load shedding, you won't see the, you would just notice shedding on the synoptic. You would not get an off light in the electrical panel. The only way you'd get this off light is if you turn the switch off, which we have. You'll notice I've depowered the utility buses on the left side. Or if there's a fault in one of the utility buses, you'll get the off light. But otherwise, during normal load shedding, you would not see the off light. But you would see it on the synoptic. It would turn amber. Normally, there's a priority logic that will shed the buses. And usually it starts from the most high draw item and then goes down from there and will reduce the power demand so it can come back in line if it needs to load shed. In normal operations, it doesn't need to load shed. But if we started to lose some buses and things like that, then the ELCUs could shed the high power draw items, which are usually on the utility and or the galley buses. Those are kind of the high draw electrical items. The priority logic, for example, may be that it sheds galley number 3, and then it sheds utility number 4, and then it sheds utility number 1, and then it reverses in the, or it comes back in the reverse order. So there is a priority logic as far as what it's going to shed and how it's going to shed it, and then it will restore in the opposite order to come back to give power to the utility and galley buses once the demand is such that it can do that. AC bus 1, 2, 3, and 4 go through the bus tie switches that are normally going to be open with the bus tie switch in the auto position, and that allows power to flow into the synchronous bus. And because these are all like power sources, they can synchronize with each other, and the split system breaker would close and everything would be in harmony on that synchronous bus. Again, you'll notice that there are drive boxes that indicate the IDG 1, 2, 3, 4. You'll also notice there's a drive disconnect switches on the overhead panel. These switches, you see these little red marks down here, they are wired closed. So it takes, when you lift the guard, you'll actually break the wire. And then it's a momentary action switch. So when you push the switch, it'll go in, but it'll come right back out. But it'll make contact, and it will then disconnect the IDG from the engine. And in that case, the AC bus would not receive power from the IDG, but it could receive power from the synchronous bus. So you'll notice if I take the generator switch for number 1 and I turn it off, the off light would indicate that the GCB is open, and by turning the switch off, that also opens the field as well. You'll notice over here on the synoptic that we have an off light illuminated. However, the AC bus is still powered because it's being powered through the synchronous bus. So we haven't lost an AC bus, and we haven't lost anything. And we haven't shed any utility buses as well. If I turn that back on, it'll close the field, and it'll arm the GCB to operate when the IDG is up to speed, which it is. So in that case, the GCB would then close and allow power to flow from the integrated drive generator, and the generator then would power the AC bus. If I take the isolation switch or the bus tie switch and I take it out of auto, I open the AC bus tie, and you'll notice it says isolation, indicating that the bus tie is open. When you do that, that'll also open the DCIR, the DC isolation relay on the DC system. And so now you notice again that AC bus 1 is still powered, but it's powered through its IDG, through its own generator. It is isolated from the synchronous bus, so you can see it's off the synchronous bus. But again, we haven't shed anything, we haven't lost any buses. It's just being powered by one source, the IDG, instead of the backup being the synchronous bus, which could also power the AC bus. Go ahead and turn that back on. When you go to auto, that will open the bus tie, the AC bus tie, and it will also allow the DC tie bus through the DCR. Actually, through the DCIR, will allow the DC tie bus to be powered. The DCIR would then allow power to go to the DC tie bus. Let's start the APU. And we'll hold it in start for 1 second and then release it to on. And normally we don't like it to spring back to on. It's a little spring-loaded switch, so when we go to start, we could release it and it would snap back to on. But they've determined over long periods of time that that's not good for the switch. And so normally when we go to start for a second, we will release it to on, but we'll still be holding it to the on position and then release our hand once it goes to on. So we're just not letting that spring load snap back to on, since that resulted in a lot of faulty switches. You notice the APU is up to operating speed now. You have an available light on APU generator 1 and APU generator 2. That means the frequency and volts are good, and they are available. Now in this airplane, it's important to note that when the APU comes up to operating speed, if we were to shut down the engines right now, 1, 2, 3, 4, and we shut them all down, the airplane would go dark. The APU does not take over automatically like it does on some airplanes. On some airplanes, when the APU is running and you shut down the engines, the APU automatically will power everything. In this airplane, it won't. It has to be selected on. So if we were just to shut down engines right now, the cabin would go dark, emergency lights would come on, and things like that. Not too good from a passenger standpoint. So we always have to make sure that APU generator 1 and or APU generator 2 are selected on before we shut down. And we'll do that here in a second. You'll notice the standby power selector is in the auto position. And remember, we said the standby power, when it's in auto, the normal power source for the standby AC bus, the main standby bus, and the APU standby bus is AC bus 3. AC bus 3 is the normal power source when this is an auto. If AC3 fails, we said it'll switch automatically to AC1, and it goes through that whole sequence of AC1 through the ground service bus, through the battery chargers, through the hot battery bus, through the battery switch to power the standby inverter, and then the standby inverter would convert it from DC to AC, and then the AC power goes to the standby bus, main standby bus and APU standby bus. If AC3 fails with a switch in auto, it'll switch to AC1, but if AC1 also fails, then the power will come directly from the battery. The battery chargers would be out of the picture, the ground service bus would be out of the picture, and the main battery then would, through the hot battery bus, through the battery switch, through the inverter, will power the standby buses, APU and main standby bus. So off is off. That depowers both standby buses, the main standby bus and the APU standby bus. Auto allows the power to come from AC3 or AC1 or the main battery in the case of failures. And if you go to the battery position, it cuts out the battery chargers, and now the battery directly will power the standby AC buses, both the main and the APU. Let's take the case where we're going to shut down, and we select APU generator 1. You'll notice that there's no green flow lines here showing that APU 1 or APU 2 is available. You just get the available lights. But that means the frequency and volts are good, so we could select APU generator 1. When we do, you'll notice that APU 1 will come online. It powers the left side of the synchronous bus. Because you have unlike power sources now, the split system breaker would open. The engines 3 and 4 are powering the right side of the synchronous bus. And if we were going to shut down and we're a freighter, we would leave it just like this, because we want APU 2 available so that they can start unloading the airplane. If this were a passenger airplane, we could go ahead and select APU generator 2 as well. It wouldn't matter because we don't have main deck handling buses and things like that on a passenger airplane. If we do shut down the engines at this time, then we will get engines 1, 2, 3, and 4 shutting down, and the drive, the constant speed drive, would wind down, and the generation would wind down, and then of course the split system breaker would close, and the APU would end up powering the whole synchronous bus. So let's take where we're going to shut them down. Let's go here and shut the engines down. And you'll notice that as the engines are spooling down, notice we get the amber indications in the drive and the generator control, because the GCB is open now and the drive is no longer operating. You notice APU 1 is now powering the whole synchronous bus, and the split system breaker is closed. And that's the way we'd want it on a freighter. Passenger airplane, we could select APU generator 2, and then the split system breaker would open, and APU 2 would power the right side of the synchronous bus, and APU 1 would power the left side of the synchronous bus. You notice there's off lights in the generator control switch because the GCB is open. You'll notice there's drive lights in the IDG because we have low oil pressure within the IDG since we shut down the engines. The drive light can come on for low oil pressure, high oil temperature, or some kind of generator frequency fault that occurs. The drive light would come on. And then we could disconnect the drive from the engine by lifting the guard and pushing the switch per procedure. So let's go up to the overhead panel, and we're going to configure for start now, so we can take a look at this. So we'll go aux. We'll leave those auto. We'll leave the fuel pumps on. We'll leave the beacon on. We'll turn 2 packs off for engine start. And leave the aft cargo heat on. The APU is running. We won't put external power on. We'll just leave the APU. We're going to start engine number 4. We're going to do an auto start. We'll just start one engine at a time. So we'll pull engine number 4. We'll bring number 4 fuel control switch to run. And of course the engine will start to rotate. And we'll get oil pressure. And we have N1. And then we have fuel flow. And we have light off. We'll go back to the electrical synoptic. And we'll take a look at what that looks like when engine number 4 comes up to speed. You can see the drive light is extinguished because the IDG is turning. When the IDG gets up to a speed, the GCB will open automatically because it's armed to do so. And then you'll notice that engine number 4 now is powering the right side of the synchronous bus, and APU1 is still powering the left side of the synchronous bus. And if we start engine number 3, nothing would change. Engine 3 would come up to speed. The generator would power AC bus 3, and you'll notice AC bus 3 is powered here from IDG number 4. So that whole right side of the synchronous bus is powered. But let's go ahead and start engine 3. And we'll go ahead and bring 3 to run. So you notice again the drive light is extinguished. And you'll notice the breaker, generator control breaker, opens. And that allows now AC bus 3 to be powered by its respective IDG. They're like power sources, so they'll synchronize with each other. And APU1 is powering the left side of the synchronous bus, and engines 3 and 4 are powering the right side of the synchronous bus. Now let's go ahead and start engines 1 and 2, and we'll do those together with auto start. And again, if we were to look at the engines here, we see that we have rotation of N2, we have oil pressure, we have N1, we have fuel flow, and we have light off. And you'll see that the drive lights are extinguished. The GCBs are going to open, and when they do so, it removes APU1, and now these power sources can synchronize to the sync bus, and all 4 power sources are like. So because of that, they can all synchronize to the synchronous bus, and the SSB will close like you see here. And notice that the APU is not on anymore, it's available. Then we could shut the APU down as part of the flow pattern. For the before taxi flow, we'd normally shut that down. And then the electrical system is back to the way it looked before when it was in flight. Okay, let's move on to some electrical questions and answers. Okay, let's answer the questions for the system study questions for the electrical system that are found in your full captain only recording section of Discord. Number 1, when does the GCB or generator control breaker automatically close? The GCB will automatically close when the IDG is up to operating speed. In order for the GCB to automatically close, the generator control switch has to be in the on position. When the generator control switch is in the on position, the field is closed, and the GCB will be armed to automatically close when that IDG comes up to speed. If you take the generator control switch and you turn it off, that will open the field and also open the GCB. Number 2, what is the normal power source for the main standby bus? Now, the normal power source for the main standby bus is AC3. And the normal power source for the APU standby bus is also AC3 through the captain's flight instrument transfer bus. And of course the backups would be AC1 if AC3 fails, and then if AC1 fails, the main battery would be the power source for the standby buses. Number 3, what occurs if available power is less than the demand? If the available power is less than the demand, you have protection in the form of load shedding. That load shedding would occur from the ELCUs, or the electrical load control units. The electrical load control units are there as protection to shed loads from the utility and or galley buses. On the freighter, you've got 4 utility buses, and on one of those utility buses would be the galley bus. There's only one galley in the freighter. And then on the passenger airplane, you would have 4 utility buses and 4 galley buses. And these are the high draw items. So if there's usually anything that's the culprit of demanding a lot of power, it would be these items that would be shed first. And of course they are shed in a priority logic determined by the ELCUs, and then they will come back in reverse order in order to restore power if that power is available again. Number 4, how will pulling an engine fire switch affect the electrical system? We actually call it a switch, not a handle. The engine fire switch, when you pull it, it does 2 things. It'll open the generator control breaker, and it also opens the field, those 2 things. Number 5, what happens when a bus tie switch is pushed off? When you take the bus tie switch and push it from auto to off, you do 2 things. You isolate the AC bus from the synchronous bus, and you also open up the DCIR, or DC isolation relay. Number 6, how are the main hot battery bus and the APU hot battery bus normally powered? The hot battery buses are normally powered from AC1 through the ground service bus and through the battery chargers in order to keep the hot battery buses powered. Number 7, what is the function of the standby bus? A standby bus is designed to protect essential flight equipment and flight instruments. If you're down to standby power only, you have 30 minutes available when you're down to that level of just standby buses. Number 8, which systems does the ground handling bus power? The ground handling bus can only be powered on the ground, and it powers the fueling panel, number 4 auxiliary hydraulic pump, and on the freighter you may have the number 1 auxiliary also, which is powered by the ground handling bus. Many airplanes just have number 4, but some airplanes will have number 4 and number 1 auxiliary pumps for hydraulics. And then you have the lower lobe cargo handling equipment, and you have the lower lobe cargo lights. And this would be for the forward cargo compartment and the aft cargo compartment. And of course on the freighter you have a main cargo deck as well, and that will have the main deck handling bus, and that's where most of the big cargo goes, of course, on the main deck, and then you have less cargo that goes in the lower lobes. So that completes the system study questions for the electrical system.